Bismillahirrahmanirrahim. Dear friends, in this video we will discuss about effective length factor. While designing the columns, there are many factors on which the column strength depends. One of the main factor is buckling. It is the geometric failure for columns. Steel columns are geometrically having thin sections compared to reinforced concrete columns, so they are more prone to buckle. While considering buckling, there is a term slenderness comes into the picture. Buckling is not only dependent upon how much the cross section of the column is thinner or thicker, but it is also dependent upon unbraced length of column. There is another factor on which this buckling is dependent, and that is support conditions of the column at its ends. Let's see this curve. This curve shows how the column strength is affected by slenderness. To mathematically measure this slenderness, there is a ratio called as slenderness ratio. It is the ratio of effective length factor K times the unbraced length L by radius of gyration R. As I have discussed that geometrically buckling depends on three factors. Number one, thin or thick cross section that is covered in radius of gyration R. The second one is unbraced length itself, and the third one is support conditions of column ends covered in effective length factor K. In AISC Specification manual, there is a table in which values of effective length factors are given corresponding to support conditions. In this table, there are 6 cases for the column end supports, and there are 2 values for each cases. One is for the theoretical purposes and the second one is for the practical purpose. And we can see that there are 4 types of supports. The first support is this one, where the rotation is fixed and translation or side sway is also fixed. Means rotation and side sway not allowed at the column end. This support is where the rotation is free or allowed, but the translation or side sway is not allowed. The third support is where the rotation is fixed, means not allowed, and translation or side sway is free or allowed. And the last one is the support where rotation and translation or side sway both are allowed. So in the first case, case A, where both the ends are having the support where rotation is fixed and translation is also fixed. This case A can be used when this type of situation occurs. Here we can see that there is a frame in which there are 2 bays. In the right bay, there is a cross bracing which prevents side sway for all the 3 columns. Alright, now all the columns are fixed at their base, but the column at the top is connected with a truss. The flexural rigidity of overall truss is very much greater than the flexural rigidity of the column. So here the relative stiffness is having a very much difference. So in that case, the top support of the column is also considered as a fixed, where the rotation is not allowed, where the column cannot easily rotate and side sway prevented by the cross bracing. Now case B can be used when this type of situation occurs. We can see that it's a frame in which there are 2 bays. In the right bay there is a cross bracing used, but at the beam column joint there is a pin support, means the beams and columns cannot transfer their moments at their joints. Alright, all the columns are having the fixed base, and this cross bracing prevents side sway for all the 3 columns. That's why there is translation is not allowed, but rotation can be allowed. Why? Because the beam column joint cannot transfer their moments, so the initial angle between the column and beam cannot be retained. Alright, now case C can be used where this type of situation occurs. Here we can see that in this frame there are 2 bays and no cross bracing is used. All the columns at their base are fixed, and at the top the same situation where there is a truss connected by the column, so the flexural rigidity of the column is very much less with compared to the overall truss. So translation is allowed because there is no bracing used for all the columns, but rotation is fixed due to the truss. Case D is used when this type of situation occurs. Here we can see that there is a frame in which there are two bays, and in the right bay cross bracing is used. All the columns at their base is pinned, and all beam column joint are also pinned. So the side sway can be prevented with the help of this cross bracings, but rotation is allowed at beam column joint because beam column cannot transfer their moments. Case E can be used where this type of situation occurs. Here we can see that there is a frame in which no cross bracing is used. All the three columns are having fixed base, but all the beam column joints are having a pin connection. It means that they cannot transfer their moments. Beam and column cannot transfer their moments. That's why rotation is allowed, and there is no cross bracing here, so side sway for all the columns is allowed. Case F can be used when this type of situation occurs. Here we can see that in this frame there is no cross bracing used. All the columns are having pin base, and at the top column is connected with the truss, so the rotation at the top is fixed, but translation is allowed. Why? Because there is no cross bracing used here. In case A, theoretical value of K can be used as 0.5, and for the practical design it can be used as 0.65. For case B, theoretical value of K can be used as 0.7, but for the practical design approach we can use 0.8. For case C, K can be used as 1 for the theoretical purposes, but for the practical one it's used as 1.2. Case D, K is also 1 for the theoretical purposes, and for the design purpose it can be used as 1 as well. For case E, theoretical value of K is 2, and for the practical design it is 2.1. For case F, theoretical and practical both, we can use K as value 2. But in case of steel frames, practically these support conditions not always exist. Let's consider a frame, rigid frame. In a beam column joint, if the beam is rigidly connected to the column, it means that moment connection is there. Then we cannot take this joint as fixed, because it is in between the fixed and the pin condition. Actually, the rigidness of the joint is dependent upon the flexural rigidity of all the members connected at that joint. In this regard, AISC specification provide calculations for the factor which accounts this effect. It is denoted by capital G. It is the ratio of flexural rigidity of all the columns by flexural rigidity of all the girders or pins connected at that joint. Since the modulus of elasticity E of the column and beams are same as steel material is used, so the factor becomes this. This factor is calculated for both the ends of the column as GA and GB. If the column support is ideal, means it's fixed or pin or a free end, then these values are used as G. For fixed, G is taken as 1, for pin, G is taken as 10, and for free end, G is taken as 1000. After calculating GA and GB factors, we can use alignment charts provided by AISC manual to find out the value of effective length factor. These charts are logarithmically scaled charts, and according to the braced or unbraced condition of the frame, we can use these charts. In this video, we will make a comparison of K values calculated by Midas Gen for a column and manually calculated K values using approach that we have just discussed.
Before getting started, if you are new to our channel, then please hit like and subscribe button and share as well with your friends, and let's learn structural engineering together. One more thing, we have already started design courses related to reinforced concrete structures and steel structures along with the steel connection design. If you did not watch those videos, then please go and watch those. Links of these videos I am sharing in the description below. So let's get started.
Let's consider this model in which we have modeled two frames in XZ plane and two frames in YZ plane. In XZ plane, the frames does not have any bracings, so it is known as unbraced frames. Whereas in YZ plane, these frames are having the cross bracings and these frames are known as braced frames. And these are the dimensions of this model. This one is 4 meter, this one is 3 meters, and this one is 2 meter. Alright, we have used W8 by 24 as beams, W12 by 16 as columns, and HSS 3 inch by 3 inch or 79.6 mm tube as bracing. Let me show you the extruded view of the frames. While considering the frame in XZ plane, the column will undergo bending about its major axis, and while considering in the YZ plane, the column will bend in their minor axis. Alright, in this case, the base is fixed for all the columns. Now, we are only designing this column for the dead loads only. Alright, let's first run the analysis for this structure and select this column. Go to Design tab, Perform Batch Design, Steel Code Check and Run. Select this one and go to Graphics, print this one. Now we can see that this one is the cross section of our column. These are the local axis Y and local axis Z. These one are the values calculated by Midas Gen for effective length factors. KY is 1.5 and KZ is 0.64. Alright, let me show you the local axes for the columns. Go to Elements and click on Local Axis. This one is the Z local axis and this one is the Y local axis and this one is the X local axis. Let's calculate K values for both the local axes of column using alignment charts. Local axes of columns are shown in small letters. First, let's find out KY. In this regard, we have to consider the frame lies in the global XZ plane, in which column undergoes bending about its major axis, means Y local axis. Let's name the column upper end as A and lower end as B. Column section used here is W12 by 16. This section name is in FPS system and we are using SI system for our calculation. Since column base is fixed, so GB is 1. For GA, we use this equation, in which IC is moment of inertia for the column about its major axis and its value is this. LC is the length of column, that is 2000 mm. IG is the moment of inertia of beam or girder about its major axis and its value is this. LG is the length of beam or girder, that is 4000 mm. When substituting all the values in the given equation, we get GA as 2.49. Now let's go to the alignment chart. Since this frame is unbraced, so we have to look into the alignment chart for unbraced frames. Mark GA and GB on the corresponding scale and join the points by a line. The intersecting K value is 1.5, hence KY is 1.5. Now let's find out KZ. In this regard, we have to consider the frame lies in the global YZ plane, in which column undergoes bending about its minor axis, means Z local axis. Since column base is fixed, so GB is 1 here as well. For GA, we have to use the same equation, in which IC is the moment of inertia of the column about its minor axis now, and its value is this. LC is same, it's 2000 mm. IG is also same because beam orientation and beam section is same in this frame. LG is the length of beam in this frame is 3000 mm now. When substituting all the values in the given equation, we get GA as 0.05. Now let's go to the alignment chart. Since this frame is braced, so we have to look into the alignment chart for the braced frames. Mark GA and GB and join the points by a line. The intersecting K value is 0.64 because at mid of 0.6 and 0.7 it is 0.65 and its intersecting point is somewhat below this, hence KZ is 0.64. Midas Gen also calculated the same values. Let's consider the second model, the second case in which all the column bases are pinned while all the other things are same as the case 1. The XZ plane frames are moment frames, YZ plane frames are braced frames. Okay, now let's run the analysis and design this column. So now we can see that KY value is 2.19 and KZ value is 0.71 calculated by Midas Gen. Let's calculate K values for both the local axes of the column for case 2 using alignment charts. Local axes of the columns are shown in small letters. First, let's find out KY. In this regard, we have to consider the frame lies in the global XZ plane, in which column undergoes bending about its major axis, means Y local axis. Let's name the column upper end as A and lower end as B. Column section used is W12 by 16. Since column base is pinned now, so GB is 10. For GA we have to use this equation in which IC is the moment of inertia for the column about its major axis and its value is this. LC is the length of the column and that is 2000 millimeters. IG is the moment of inertia of the beam about its major axis and its value is this. LG is the length of the beam and that is 4000 millimeters. When substituting all the values in the given equation, we get GA as 2.49. Now let's go to the alignment charts. Since this frame is unbraced, so we have to look into the alignment chart for unbraced frames. Mark GA and GB and join the points by a line. The intersecting K value is 2.2, hence KY is 2.2. Now let's find out KZ. In this regard, we have to consider the frame lies in the global YZ plane in which column undergoes bending about its minor axis, means Z local axis. Since the column base is pinned, so GB is 10 here as well. For GA, we use the same equation in which IC is the moment of inertia of the column about its minor axis now and its value is this. LC is the length of the column that is same 2000 millimeters. IG is the moment of inertia about major axis of the beam and its value is this. LG is the length of the beam and in this frame it is 3000 millimeters. When substituting all the values in the given equation, we get GA as 0.05. Now let's go to the alignment chart. Since this frame is braced, so we have to look into the alignment chart for the braced frames. Mark GA and GB on the respective scales and join the points by a line. We can see that mid of 0.7 and 0.8 is 0.75 and the intersecting point is nearly about 0.71, hence KZ is 0.71. Midas Gen also calculated nearly about same values. Let's consider the third case in which in this model I have deleted the cross bracings and all the column bases are fixed. Alright, so in this way all the frames are unbraced. So go to the design tab, general design parameter definition of frame. In X direction it's unbraced, in Y direction is also unbraced. Now let's run the analysis and let's design this column. Now we can see that KY is 1.5 and KZ is 1.17. Now we will calculate K values for both the local axes of columns for case 3 using alignment charts. Local axes of columns are shown in small letters. First we find out KY. In this regard, we have to consider the frame lies in the global XZ plane in which columns undergoes bending about its major axis, means local Y axis. Let's name the upper end of the column as A and the lower end as B. Column section used is W12 by 16. Since the column base is fixed here, so GB is 1. For GA, we'll use the same equation in which IC is moment of inertia of the column about its major axis and its value is this. LC is the length of the column and that is 2000 millimeters. IG is the moment of inertia of the beam about its major axis and its value is this. LG is the length of the beam and that is 4000 millimeter. When substituting all the values in the given equation, we get GA is equals to 2.49. Now let's go to the alignment chart. Since the frame is unbraced, so we have to look into the alignment chart for unbraced frames. Mark GA and GB and join the points by a line. The intersecting K value is 1.5 and hence it is K by 1.5. Now let's find out KZ. In this regard, we have to consider the frame lies in the global YZ plane in which column undergoes bending about its minor axis, means Z local axis. Since the column base is fixed here as well, so GB is 1 here. For GA, we use the same equation in which IC is the moment of inertia of the column about its minor axis and its value is this. LC is the length of the column and that is 2000 millimeters. IG is the moment of inertia of the beam and its value is this. LG is the length of the beam in this frame is 3000 millimeters. When substituting all the values in the given equation, we get GA as 0.05. Now let's go to the alignment chart. Since this frame is also unbraced, so we'll have to look into the same alignment chart. Mark GA and GB on the corresponding scales and join the points by a line. We can see that the intersecting point is nearly about 1.15. Hence KZ is 1.15. Midas Gen also calculated nearly same values. Now consider this last case in which I have considered only one frame in XZ plane and deleted all the rest frames. Alright. In XZ plane, the columns of this frame is considered as unbraced, and in YZ plane, since there are no beam in YZ plane joining the column, so in YZ plane the column is behaving as a cantilever. So in both the directions the column is behaving as unbraced column. And let's first just analyze the frame and steel code check. Now we can see that in this case KY is 1.5 and KZ is 2.31. These values are calculated by Midas Gen. Alright. Since the column in YZ plane means in local Z bending, the column is considered as cantilever column, and we know that according to this table of AISC manual, case E, there is a cantilever column and at the free end rotation is free and translation is also free. This is our case, so that's why case E. The theoretical K value is 2 and recommended design value while ideal conditions are approximated. We can consider the K value as 2.1. Alright, but Midas Gen is calculating the value 2.31, so we can actually override this value by manually inputting that in KZ as 2.1 and proceed the design procedure. So now go to the design tab, select this column, these columns, and go to general design parameters, effective length factors, and now we want only to override the KZ value but not KY. But in Midas Gen, if you are manually overwriting these K factors, so we have to put both these values. Alright, so let's just check what is the KY value calculated by software. It's 1.5, so KY put it 1.5 and KZ is 2.1 and apply on the design. Okay, so now we can see that KZ value has been overwritten. If we consider KZ value as 2.31, so the slenderness ratio will be more conservative. Alright, but we cannot go beyond 2.1 value, so that's why we have overwritten this one and proceeding the design. Now for the last case, case 4, we will calculate K values for both the local axes of the column using alignment charts. First for KY. We know that the frame is unbraced, so we have previously calculated ky as 1.5. Now for kz, since no beam is connecting this column, hence the column is considered as cantilever in its minor axis. Since column base is fixed, so GB is 1 here. For GA, let's see the same equation. As we know, there is no beam connecting the column, so IG is 0, means the moment of inertia of the beam is 0. Any number dividing by 0 will give infinity, so we get GA as infinity. Now let's go to the alignment charts. Let's consider this case as unbraced frame, even though there is no frame in this direction, so we'll look into the alignment chart for unbraced frame. Mark GA as infinity and GB as 1 and join the points by a line. We can see that intersecting point is nearly about 2.3, hence KZ is 2.3. And we know that Midas Gen has also calculated the same values, but we can override KZ as 2.1. The reason for explaining the concept of effective length factor is that we can be confident about the values calculated by the softwares. Because in the structural design, whatever software will be used for the calculations, main thing to remember is garbage in, garbage out. So it is necessary to keep an eye on the calculations made by the softwares.
So this is it for today. In the next videos, you will see some other interesting content related to structural engineering. If you like our video, then please hit like and subscribe button and also share with your friends. You can comment below for your desired content or desired topics. I will try to make that content for you. So see you in the next video.